Okay, so what can we infer from these 30 weights? Well, the one tool we have right now is the single proportion confidence interval. So we can take a look at our 30 weights, and we can notice that if we compare them to half a pound, it looks like 7 of them are under half a pound, which means 23 of them are half a pound or more. And we could use the one tool we have available to us to look at the percentage, I guess, of those that are half a pound or more. And when you look at it, the percentage is well above 50%, even considering the margin of error. So that's one way of thinking about it. We can look at the percentage. But the thing about it is that's not what their claim is. Their claim is the burritos are half a pound. Now, clearly some of them aren't, because I just weighed a few and some of them weren't. But I guess typically are they half a pound? And then that's got me thinking that maybe the percentage isn't the right tool to use, because a percentage just says if something is or isn't. It doesn't actually talk about its value, which makes me think that we shouldn't be looking at proportions at all. Maybe we should be looking at averages. This is the first kind of example that we've seen so far where we're not trying to estimate the percentage of something happening, but the actual average of something. So in other words, if we've gone from discrete data that's countable to continuous data that's measurable, which makes perfect sense. I had to measure these burrito weights. Awesome. Okay, my friends. So far, we've been trying to estimate the parameter, and the only one we've got so far is the unknown parametric proportion, which we call little p. The statistic that we use to do that is p hat, and the margin of error from last week is built around that p hat, and also the sample size and also the confidence multiplier. So the sample size is exactly what it sounds like. It's how big your sample is. The confidence multiplier, that z out there, is dependent on how confident you want to be. We usually use 1.96 for 95% confidence and so forth. And the p hats are all gotten from within the study itself, the number of successes over the sample size. Beautiful. And then down here is the punchline, of course, that you are confident that the proportion you're looking for in the population is trapped between p hat plus or minus the margin of error. Excellent. Now, the catch now is we no longer are looking at a proportion. We want to look at an average with an unknown mu. Okay, so we need an average. In the population, that average is the Greek letter mu. It's just a fancy Greek letter that means it's the population average you're never going to know. So somewhere out there in the world of Del Taco half-pound bean and cheese burritos is the average weight, which we're never going to know because we can't weigh them all. Best thing we can do is get a sample and pull the statistic from that sample. So the statistic for an average is X bar. Now you remember this guy from, I don't know, week 2, week 3, somewhere back then. You just add up all the data and divide by how many data points you have. So this is going to look somewhat similar. It's actually related to the proportion, except instead in the proportion you're simply counting how many things have a property and dividing. Here you're actually adding them up and dividing, which spreads them out evenly, and you get the idea of the typical if all the data were equal measure of center. Okay, now the challenge becomes in the margin of error. And we're going to build this up from first principles, so to speak. Margins of error, if you remember back, start from standard error, and then they have a multiplier applied to them. Standard error from the central limit theorem is found by looking at the population standard deviation divided by the square root of the sample size. This shows up in the proportion standard error too. It just doesn't look quite the same as it's going to look here. The population standard deviation, I'm just going to put that as STDEV. This is only going to be here temporarily. The standard deviation in the population is little sigma. Don't memorize this because it's going to be gone soon. And by the central limit theorem, the standard error is that divided by the square root of the sample size. Well, the problem with that is we don't know what that is, because in order to know what that is, we'd have to also know what mu is, and we don't know that either. But there is a measure that we can substitute in for the population standard deviation. It's the sample standard deviation, which we learned about in week 3, I believe. And we call that, dear friends, little s. Little s. Now, that right there is the standard error for that statistic. So, we can calculate this based on the sample, and we can calculate this based on the sample. We will soon enough with Del Taco for starters. And then we can add and subtract that from the sample mean. The only problem with that is, since it's only one standard error, it's going to be 68% confidence or something around those lines. It won't be confident enough. So, we got to turn this into a margin of error. Well, a lot of hand erasing. Look at that. Margin of error, which means, I'm going to write one more thing I'm going to erase. We need a confidence. Can't believe I'm writing this out just to erase it. We need to have a confidence multiplier. Now, in proportions, we used Z, the bell curve standard deviations. But with the average, there's some history we're going to look at here in this next video. You don't have to memorize the history. It's not a history class. But I find the history interesting because of what you're about to see in the margin of error calculation for that confidence multiplier. It's not Z. It's not the bell curve. Well, it is a bell curve. It's just not the Z curve. It's known as the T curve. So the T multiplier is what you multiply by the standard error to get whatever level of confidence you need. Okay, you're probably pissed off at me right now, and that's okay, justifiably so. Let's do a video kind of talking about the history of why T and not Z. Let's go take a look.